Hello, my name is Hongming Liu. I'm a PhD student in Shanghai Jiaotong University. My interest is focusing on invariant generation. Invariant generation is a classical problem to automatically generate invariants to aid the formal analysis of programs. In the literature, the only known sound and complete characterization to solve this problem is via Farkas Lemma. Although Farkas Lemma-based approaches can generate highly accurate linear invariants, the main bottleneck to applying these approaches is a scalability issue caused by combinatorial explosion. We base our approach on the only practical Farkas Lemma-based approaches and develop several novel and independent improvements to leverage this scalability. We consider linear transition systems as the underlying model for invariant generation. A LinTS is a tuple where X is a finite set of real-valued variables, such that each variable ij represents the current value of the variable. L is a finite set of locations. T is a finite set of transitions, where each transition's toll is a triple L prime row that specifies the jump from the current location L to the next location L prime with a guard condition rho. Theta is a linear assertion that specifies the initial condition as the initial location L0. Informally, an invariant at a location is a logical formula that is always satisfied by the values of the variables whenever the location is entered by some path. Informally, for initialization, a LinTS starts its initial location with an initial valuation such that theta implies eta. Then for consecution, the LinTS determines the next configuration by first selecting the transition. Below is a tabular form of the Farkas lemma.
I think we are missing the slides. We see the same slide all the time.
Sorry?
I think, okay. The slides were not moving, but now we are at the right slide. Thank you.
Well, okay, sorry, hold on, please. Am I right now? Is a full screen slide now? Can these slides moving? Here is the motivation slides, right?
We are still seeing the slides with the overview, and we are only seeing the first slide.
Okay. Maybe I just use these slides. Okay. I use this.
Okay, but you also need to move on a little bit because we are running behind.
Sorry, I directly moving these slides.
Motivation, okay.
Okay, invariant generation is a classical problem to automatically generate invariants to aid the formal analysis of programs. In the literature, the only known sound and complete characterization to solve this problem is via Farkas lemma. Although Farkas lemma-based approaches can generate highly accurate linear invariants, the main bottleneck to applying these approaches is a scalability issue caused by combinatorial explosion. We base our approach on this only practical Farkas Lemma-based approach and develop several novel and independent improvements to leverage this scalability. We consider linear transition systems as the underlying model for invariant generation. A LinTS is a tuple where X is a finite set of real-valued variables such that each variable ij represents the current value of the variable. L is a finite set of locations. T is a finite set of transitions where each transition tau is a triple L prime row that specifies the jump from the current location to the next location with a guard condition. Theta is a linear assertion that specifies the initial condition at the initial location L sub 0. Informally, an invariant at a location is a logical formula that is always satisfied by the values of the variables whenever the location is entered by some path. Informally, for initialization, a LinTS starts at its initial location with an initial valuation such that theta implies eta. Then for consecution, the LinTS determines the next configuration by first selecting a transition. Below is the tabular form of the Farkas lemma. Consider a scenario of a Vagrant robot. The control of the robot works in two alternating models modeled as two locations L sub O and L sub 1. Each model takes a time between 1 and 2 seconds. The standard approach first establish a template eta L sub O and eta L sub 1. Then it simplifies the initialization and consecution conditions. For the initialization, we have that the results in the constraint C sub LO1 equals to lambda 1, and so on, and D sub LO greater than or equal to O. After projecting away the fresh variable lambda, we obtain D sub LO greater or equal to 0. For the initialization, next, for the consecution conditions, we present the tabular form for the transitions, and the lambda are eliminated by the projection polyhedral projection, while the fresh variable mu is eliminated by the heuristic guessing values, which is based on some practical rules such that setting mu manually to 0 or 1. The transition tau2 is treated in a similar way. After removing mu and lambda, the resultant constraint is a conjunctive normal form formula where each automatic proposition is a polyhedral cone over the unknown coefficients. The approach further expands the CNF equivalently into a DNF formula. For this example, one disjunctive clause from the DNF formula is shown. By computing the generators of the polyhedron cone, we obtain the corresponding generators and their corresponding invariants, where in the left part each row specifies a generator, and in the right part we instantiate the generator into the unknown coefficient in the template eta to obtain the invariant at the location LO and L1. The obtained invariants are further minimized. It happens that the invariants above coincide with the ones from the whole DNF formula. However, the main weakness of the standard approach is that the CNF-to-DNF experience still leads to a large amount of combinatorial explosion. In order to further reduce combinatorial explosion, we complete the standard approach with several ideas. The following subsections illustrate the main ideas of our improvements. In the generator computation, we eliminated variables unrelated to the target location in advance to speed up the generator computation. In the CNF-to-DNF experiment, we reorder the experiment so that the target location comes first to detect subsumptions earlier. Our third improvement is logical segmented subsumption testing that serves as a pre-processing for the CNF-to-DNF experiment and could detect local subsumptions in advance. In summary, we divide the whole conjunctive clause C1 and C2 and so on and Cm into a number of segments and perform local subsumptions testing. In practice, we keep the size of each segment small to avoid the combinatorial explosion from the expansion of each segment. Experiment results show that our improvements can improve the scalability of the standard approach by orders of magnitude. Thank you so much for watching. Okay, I'm here. Any questions?
Thank you. I have a question. Does the presentation was went quite deep into how the invariant generation works? Is the technique restricted to the case where we have the invariants are just about variables? Is it applicable where the invariants might be talking about arrays? Is it applicable where they might talk about graphs and objects in the graphs? I couldn't get how general the question was, and also would it be applicable if in the invariants we would like to mention predicates like the list is acyclic or stuff like that.
Okay, if you ask the invariant generations, this work is mainly follow the 2003 paper, which is based on the Farkas Lemma, and in that paper, it mainly used the Farkas Lemma to solve the invariant generation with a template, and which
invariant generation with what?
With the Farkas Lemma theory in the 2003. Yes. Yeah, there is a paper.
Yeah.
In that paper, in that paper, it realized first establish a template which is focused on the invariant, and then use the Farkas Lemma to solve this inductive invariant. And in our paper, we only focus on the speed up. Yes, we just to reorder, such as reorder or the projection, which is only focused on the generator's computation or the conjunctive normal for to disjunctive normal force the expansion order. Yes, with this paper, with this work, we just only focus on the speed up. It's optimal. It's our optimization.
I realized that the paper was based on the Farkas result, and that you have made it faster. But I do not. I was asking whether the original result was to what kind of invariance it was applicable. Whether the invariants were just talking about variables. For instance, if I want to prove that a loop calculates the greatest common divisor, I just need variables. Or whether the invariants also can talk about arrays, or can talk. What kind of things appear in the invariants that you are generating?
Yes, it's for the loop. Is a loop program or in the conjunctive loop invariant. If there is a disjunctive loop program, is not due to our work. We only focus on the conjunctive program.
Right. So what? Okay. What kind of can you deal with programs that can your invariants deal with programs that contain arrays? Or could the technique be expanded to deal with programs that contain arrays?
Oh, sorry. Here I maybe it's a wrong network. Pardon, please.
Okay. I was wondering, I was going back to this. Could you generate, with your approach, could you generate invariants for a program that had arrays? For instance, a loop that goes through an array and finds the maximal number in the array?
No, maybe we'll not focus on this, area.
Okay. All right. Thank you. I wanted to understand, to get a better idea of the applicability. Yeah.
Okay.
Thank you.
Thank you.
Thank you very much. The speed ups were impressive that you have been showing us.